Hello, I'm Charlie. This video is about the first paper of my PhD called One-Shot Learning for MIPs with SOS1 Constraints. It was published in Operations Research Forum, July 1st, 2024. It's about the locomotive assignment problem, LEP. It's a large-scale problem for the Canadian National Railway Company. Our strategy revolves around the special ordered sets of type 1, which I will call SOS1 constraints for short. These constraints are used to represent the assignment of a set of locomotive to a train in the network. The problem formulation can be represented using the following notation, where we start with a generic MIP, which is linear, and then we add these constraints, the SOS1 constraints. These constraints are modeled using a sum over a set of binary variables, and each binary variables represent a different assignment, and only one assignment can be chosen from the set. The methodology is called probe and freeze. It's a one-shot learning heuristic, which means that all learning happens online. It's divided into 3 steps: probe, select, and freeze. And we will explain each of these steps in the following slides. Probing is about collecting data from the top of the branch and bound tree. At every node, we compute the most likely class based on which variable has the highest value. To do so, we compute an argmax over the values of x, and then we concatenate that information in the value vector kv. Selection happens with an entropy measure, so H. The H measure gives us some information about the uncertainty associated with the data that we got. This is the entropy idea of this paper, where I give here 2 examples of, let's say we have train A and train B. For train A, most of the time in the branch and bound tree, we see that x2 is being selected and x1 some of the time. Whereas for the second train, train B, the distribution is more spread out. If you compute the distribution or the entropy of that distribution, you would find that A is less uncertain than B, or has less entropy. And to reduce assignment risk, we select constraints with low entropy. This is compatible with what is intuitive here. You would want to fix the train for which it's less uncertain what is the optimal assignment. The last step is about freezing constraints, where we explicitly force the solver to choose a given assignment. We compute that most likely class with an argmax over the distribution, and we fix it with the following constraint. We work with 2 different data sets, LEP A and B, where in the first case we have smaller instances with a small time limit of about 10 minutes and 300 trains. In large instances, they contain all the trains in the network, more than 5,000, and we give each instance 6 hours of compute time budget. Here are the results for the probing data. So how many nodes do we find during the branch and bound? I want to bring your attention to skip, where we have about 20 nodes being selected or found during the first 2 minutes, whereas Cplex generates more than 1,000. This is important because this has important impacts on downstream performance, since we rely heavily on that data to make high-quality solutions. In particular, we found that skip had very poor performance relative to the other 2 solvers. Here are the primal gap results, where we show how good each different algorithm perform with respect to the best known solution. We can look at the column wins to see which algorithm performs best. We can see that for LEP-A, the best performing algorithm is PNF with these configuration. The second best is Cplex with 7 wins. We also tried different LNS heuristics, RINS and LB, but didn't perform as well. We also experimented with LEP-B, the big instances. Once again, PNF outperforms the alternatives. For RINS and LB, we don't have any results because they rely on a feasible solution. And during the probing time, we didn't find any feasible solution for these instances. PNF in this configuration finds 7 wins. Actually, it wins on all of these 10 instances that we had, and Cplex has 0 wins. And we can see quite a big gap in terms of performance between PNF and Cplex. So our method is most effective on large instances. Here are the results on MIPlib. MIPlib is a diverse set of instances that is open source. And here the performance shows a slightly different story. We still get the best performance with a PNF configuration. The second best is Cplex once again, but the performance difference between the methods is not as significant. This can be mostly explained by the fact that we have a wide diversity of instances in this data set. In this paper, we propose a novel combination of entropy and LNS for MIPs with SOS1 constraints. It can be easily integrated into existing solvers. Its performance depends on the amount of probing data available. Initial branch-bound solutions can be good proxies for high-quality solutions. And PNF tend to outperform alternative NLS heuristics on LEP instances and a subset of MIPlib instances. Thank you for watching. Bye-bye.